Okay, now we try and calculate the lower critical field of a type 2 superconductor. If you recall that a type 2 superconductor, if you look at the image of a type 2 superconductor, the magnetization versus the field behavior, then if you recall that it was up to lower critical field, the prior to the lower critical field HC1, so this is HC1, this was in the Meissner state, namely B was equal to 0. Okay, however, just above HC1, okay, the vortices start entering into the superconductor and then your magnetization starts to decrease. Okay, and of course it goes up to HC2, but the main thing is that up to HC1 the system is in the Meissner phase where B is equal to 0, and above vortices appear in the superconductor. Above HC1 vortices begin to appear in the superconductor. So how do we calculate HC1? So HC1 is at the point where HC1 is the field separating no vortex state, namely B is equal to 0 Meissner state, and a superconductor with a vortex in it. So it just is the boundary between, so on this side you have a superconductor, on this side you have a superconductor without any vortex. Okay, here B is equal to 0, and on this side just above the upper critical field, so on one side you have a superconductor without a vortex, and on the other side just above the lower critical field you have a superconductor with a vortex which is created inside it. Okay, so the lower critical field HC1 actually separates these two states. Okay, on one side you have a superconductor with no magnetic field inside it, and on the other side you have a vortex which is created inside the superconductor. So how does one describe such a state? Okay, so the lower critical field HC1 is obtained by requiring that the Gibbs free energy of the Meissner state with no vortex, Meissner state with no vortex, be equal to the Gibbs free energy of the superconductor with one vortex inside it, because that is what is happening physically at the lower critical field HC1. What is happening is that it is distinguishing a state which has no vortices inside it, a Meissner phase with no vortex inside it, and a phase which has just one vortex inside it. So the energy, the Gibbs free energy at that point becomes exactly equal. The energy of a vortex state with no vortices and the energy of a state with just one vortex becomes exactly equal. So that is the point at which you will have the lower critical field, and that is what we will use, and we will use this to actually calculate the lower critical field. Now let us consider a superconductor with just one vortex. You have a superconductor with one vortex which is created here. This is the length of the superconductor. The thickness of the superconductor, or the length of the vortex, is L, which is also the length of the vortex L, which is present through the superconductor. Now the Gibbs free energy of the superconductor with one vortex, which is, let's say, GO, is equal to the free energy of the superconductor without vortices. Naturally, this is just the free energy of the superconductor without vortices plus the energy of a vortex line minus integral B dot H d cube R. Okay, this is the free energy of the superconductor. This is the Gibbs free energy of the superconductor with just one vortex, which is the free energy of the superconductor without vortices plus the energy of a vortex line and minus integral B dot H d cube R. Okay. Now energy of the vortex line, the energy of vortex line will be nothing else but E naught into L, where E naught is the energy per unit length of a vortex, and this was equal to phi naught square by 4 pi lambda square mu naught log of lambda by xi. If you recall, this was phi naught square, the flux quantum phi naught square by 4 pi lambda square mu naught, 4 pi lambda square mu naught log of lambda by xi. Okay, and L is the length of the vortex. This is the energy per unit length. Epsilon naught is the energy per unit length of the vortex. So this energy of the vortex line will become epsilon naught into L will become phi naught square into L divided by 4 pi lambda square mu naught log of lambda by xi. And the other energy integral of B H, which is the natural contribution which you have inside the Gibbs free energy. So this integral term B dot H term d cube R at H equal to HC1 will be nothing else but integral of B into HC1 d cube R. Now this would be HC1 into B d cube R. Okay, now the B is non-zero, the B is equal to 0. Remember, B is equal to 0 everywhere except around the vortex. Okay, so this integral d cube R, which is integrated over the entire volume of the superconductor, integral B d cube R integrated over volume of superconductor, will have contribution only from around the vortex, and integral B dot d cube R, integral B dot d cube R, B d cube R can be written as nothing else but L into B ds, okay, and over the entire superconductor B dot ds will be the magnetic flux phi naught, since there is a single vortex in the superconductor. Okay, recall that you have a vortex, recall that you have a superconductor. Recall that you have a vortex which is carrying fixed quantum of magnetic flux, and this is the flux which is associated with the entire superconductor. So even if you integrate this over this is integral of B ds over the entire superconductor, it is going to be equal to phi naught, because phi naught is the only magnetic flux present inside the superconductor. So this will be nothing else but L times phi naught. So the integral of BH dq bar will basically become hc1 into L phi naught. Okay, this would be essentially hc1L into L phi naught. Okay, so your Gibbs free energy of the, so if you go back to the above expression, if you go back to your above expression of the Gibbs free energy with one vortex G0, it is equal to the free energy of the superconducting state. So the G0 one vortex superconductor G0 would be the free energy of the superconductor plus epsilon naught into L minus hc1 into L phi naught. Okay, this is the energy of a superconductor without a vortex, with one vortex, and Gs is the Meissner state at hc1 with no vortex equal to 0. There are 0 vortices inside this state, so it is just separating a state with no vortices and a state with just one vortex, and this energy will just be equal to Fs. Okay, because this term, because with no vortices this term will be 0, and with no vortices the flux quantum inside the superconductor will be 0. So when you consider Gs equal to G0 at H equal to Hc1, okay, that is the free energy difference between the superconductor with one vortex and a superconductor with no vortices is Hc1, then you will get Fs is equal to Fs plus epsilon naught into L minus L into Hc1 into phi 0, or this would imply that Hc1 is equal to epsilon naught by phi 0, which is equal to phi naught by 4 pi lambda square mu naught log of lambda by xi. This is your calculation of your lower critical field of the superconductor, where Hc1 for a typical type 2 superconductor, especially in the extreme type 2 case, 4 pi lambda square log of lambda by xi. If it is not in the extreme type 2 case, there are a few higher order corrections which we had seen in the earlier. There are a little bit more corrections, but they are basically of this order: phi naught by lambda square. This log lambda by xi is the contribution, and then there are because of the magnetostatic energy term that can also contribute to this, so it will just add on to this expression. But Hc1 basically would be of this form. Okay, and this is your lower critical field of type 2 superconductor, which separates a state with no vortices from a state where one vortex has been created inside the superconductor.